welcome everybody. Thank you for coming. So it's the seminar, one quick announcement, which is on Friday, the seminar, Javier Rodriguez, this seminar, which was going to be at 3, we moved to the morning. It's going to be at 11. I'll say this again in an email later today, actually. Maybe just make a mental note of it in the morning on Friday, not in the afternoon. So our speaker this morning is Jess Johnson from the School of Environmental Sciences here at the University of East Anglia, which is going to speak on multiphase fluids and around volcanoes.
Brilliant. Thanks for the introduction. So my name's Jess. I am a volcano geophysicist, and I've spent the vast majority of my professional life studying volcanoes and basically trying to work out what's going on under the ground. And it's not an easy problem. So what I'm going to do today is talk through, give you a quick sort of 101 on what volcanoes are, how we understand them, and talk about the observations that we can make around volcanoes and some of the modelling that we're doing at the moment, but in particular where there's a lot of challenges still left to explore. So this is a sort of an overview of what I'm going to talk about today. This is a sort of cartoon of a volcano. We have a magma reservoir containing liquid, gas, and crystals. Then the magma gets to the surface somehow. We've got lots of phase changes happening as that's going on. And then we have eruption. So lots of interesting things going on actually at that point of eruption. And then in the air, sometimes we have a combination of gases, ash, sometimes we've got lava flows and various other things as well. So I'm going to talk, I'm going to go from bottom to top. So I'm going to talk about accumulation, then ascent, then eruption, then dispersal. And then I'm going to give you a case study with some what we call volcano corn at the end, if I have time. So what happens underneath a volcano? Well, this is a cartoon that, if you think back to your GCSEs, you may have learned about a magma chamber. We don't call it a magma chamber anymore. Sometimes we still model it as like a nice spherical bubble, but that's not actually what's going on under the ground. This is more what's happening. We've got kind of this area in the crust that transitions to the mantle. We've got bits of liquid coming up, but it's not just liquid. And then we've got lenses of melt combined with various bits of crystals and gas. There's a lot of gas dissolved. There's gas dissolved in fluids, but then in the liquids. But at the same time, there are bubbles as well. The liquid itself has various properties. It's not Newtonian. It's the viscosity varies with the bubbles, the shape of the bubbles, the temperature, the number of crystals, the shape of the crystals, and things like that. So lots and lots going on. But why have we changed the way that we think about volcanoes? Why can't we just use this bubble image? So I'm going to take you through some of the evidence that we have. So this is a sort of conceptual model of what we think is going on inside of these reservoirs that we're having now. So we have primitive melt. So this is what's coming from the mantle. And it's coming up and it's trying to make its way through all of these crystals. There's some cooling going on at the same time. So these crystals are forming, growing, sometimes capturing some of the liquids, sometimes capturing bubbles in them as well. And so if you have an injection of magma from deep into a reservoir, then what we'll find is as it cools, you'll end up getting a settling of crystals. And so we have what is called a mush region, where it's more solid than liquid, but not solid. But then sometimes we also get another injection of a hotter, more primitive melt, and that swells things up a bit. And then sometimes if it's left, if it doesn't have another injection of melt from deep for a long time, the crust will deform, and that magma reservoir might cool, it might solidify slightly, and it will be deformed. And so you get sort of stratification within that, where the crystals themselves can deform, or the sort of assemblages can deform as well. And so we get this accumulate in terms of the actual geology. Now, I'm not a geologist, so I can't answer lots of questions about the geology, but here we have some geology. So this was the first clue that geologists had, that things weren't completely simple. So some of these are eruptive products, and some of these are products that, so if anyone can remember back to their sort of GCSEs, A-levels, there are two types of igneous rock. There are the rocks that have been erupted, we call those extrusive, and there are rocks that cool in the crust that never get erupted, and those are intrusive. So some of these are extrusive and some of these are intrusive. But what we see is lumps of other stuff. So on top here, you've got what we call an enclave, and that's kind of like a lump of a more primitive magma that got sort of injected into this rhyolite, in something that's old, it's been sitting there for a long time, it's very sticky. But this enclave of more or less viscous, younger material, you can tell by the colour that the older materials tend to be lighter grey, the younger materials tend to be darker grey, black, because of the silica content in them, because as the crystals form, different materials get taken out. And so you can see these enclaves where there's not been mixing, and then we can go all the way down to kind of microscope scale, where we can see these crystals and look at how they've grown. So here you can see there's a crystal of pinopyroxene, which grew slowly in the magma reservoir under the ground, but then there's this kind of rim of something that got quenched really quickly. So that indicates that it's being erupted, and it's sort of solidified really quickly, and you can see it's really, really fine grained, and then this is really bubbly around the outside, because I'll talk about eruption later. So that's some of the kind of the hand geology, and then this, again, I'm not going to go into this too much, but if you cut your rock really thin, look at it under a microscope, and then use polarized light, then you get beautiful colours. And the different colours tell you about different materials, different crystals, different minerals within the rock. And I'm not going to spend too much time on this, but one of the interesting things is you can see the interaction between the crystals that have been forming underground for a long time and new melt. So sometimes the melt will thermally erode the crystals, sometimes those crystals will grow, and they have like tree rings almost, where you can see the periods that they've been growing, and they have different chemistry in each of those tree rings, so you can see the chemistry of what's been injected. So you can see this mixture of crystals and bubbles and liquid in the rocks that we get on the surface. But that's on the surface. What about what's going on under the ground? Well, this is where I come in. I am a seismologist, so what that means is I use earthquakes or earth vibrations to try and work out what's going on under the ground. And this isn't my work, but one of the things we can do is use small earthquakes. So there are lots of small earthquakes around volcanoes all the time. So small that you can feel them, but we can measure them. So we can take the small earthquakes, we can look at the time it takes for the seismic waves to get from where the earthquake was to our sensors, and we can essentially do a CAT scan. So it's tomography, same with CAT scan, and we can do like a big matrix inversion, and we can work out the seismic velocities of each of these cells under the ground. And we know that Seismic S waves, the shear waves, don't travel through liquids and fluids. P waves, pressure waves do. The P waves are faster. But we also know that if there's a material that has like a liquid in the pore spaces or is partially melted or things like that, it generally has a slower seismic velocity. So we can use a combination of P wave speeds, S wave speeds, and a ratio of P wave speed to S wave speed to make an image that shows us what's going on under the ground. Now, it's not great. We don't have great resolution. It depends on the number of earthquakes we have. And obviously, a lot of the earthquakes are happening in the crust. Very few earthquakes happen in the mantle because it's plastic rather than brittle. But what we can see is there are definitely areas that have higher seismic velocity, lower seismic velocity, my bad, underneath the peak of the volcano. So we can combine that with different types of imaging, we can combine that with what we've learned from metrology and geology, and we can say that we've got these kind of layers with regions around them. So there's a very slow bed, and then areas around, yeah.
Just a small question,
yeah.
How many sensors do you use in order to make seismography typically?
On some of the best monitored volcanoes, we're talking 20.
20.
Is this Mount St. Helens? This is Mount St. Helens. There was a big project in Mount St. Helens where they put hundreds of these new nodes. They don't have as much of a broadband response, so you can't see some of the low frequency earthquakes. But the point was they wanted to do a really high resolution tomography. So you can get better resolution, but yet the really well monitored volcanoes only have 20 sensors on them, and they're not always positioned for this type of work. They're more positioned for monitoring. So sometimes you do have big gaps where we don't get good resolution. Anyway, so this is the interpretation. And these are some of the knowledge gaps that we can't see using this method. So there are lots of them. And here's a completely different method, also geophysics, magnetotellurics. So the way this works is we have a coil of wire, we lay it out on the ground, and we use naturally occurring variations in the electromagnetic field. So this could be, if we're talking about high frequencies to look fairly shallow, we're talking about lightning strikes or lightning occurrences. We can use weather, but more frequently what we use to look a bit deeper is the rotation of the Earth inside the magnetic field. Because of the solar wind, the Earth's magnetic field is kind of like a teardrop shape. So the magnetic field lines are closer together in the daytime and further apart in the nighttime when we're facing away from the sun. And so that variation in the Earth's magnetic field creates electromagnetic waves in the ground at a very long period, and we can see deep. With this method, it's really cool. If you leave your coils there for long enough, you can actually see into the Earth's core because of the 11-year sunspot cycle as well. But we're not talking about that. This, we're looking to sort of 20 kilometers depth, and when you have a magmatic system, basically this is showing you the conductivity. And the red here is showing a low conductivity, and the blue is showing a higher conductivity, which is maybe potentially counterintuitive, but magma is actually very low conductivity. And the rock elsewhere is more likely to have water in it. And water with things dissolved in it is a better conductor. So here you can see again, you've got these kind of pockets of bright red, which is great, and then you've got this yellow area around it. And that again is evidence that we've got this kind of partially solid, partially fluid area. We can also see that it has to be magma accumulating under the ground because the ground moves. And so here's an example. This uses satellites. It's a technique called interferometric synthetic aperture radar, INSAR for short. So it has one radar image when the satellite goes over next week or whenever it is. Satellite goes over again, takes another image from exactly the same place. And if the Earth has moved slightly towards or away from the satellite, if you overlay those images, you get an interferogram. So so here we're basically seeing this bullseye, and this bullseye tells us that this bit here has risen by, I've not got a scale here, 20 centimetres. Yeah, so that bit in there has probably risen by a good 20 or 30 centimetres in the time that these two images were taken, which is actually quite a lot. You wouldn't feel it if you were there, but in a week or so, 20 centimetres, 30 centimetres is quite a lot for the ground to come up. And so we can do pretty simple modelling, and like analytical models of this have been around for a century. And we have this model where magma is accumulating somewhere, but that's pretty much as far as it goes. The state of the art of these models, we can now include like a viscoelastic shell around our bubble of magma, and we are including things like thermal gradient as well. So you know, the analytical models, they assume a completely elastic, homogeneous, whole space of rock. We can build on that, we can make it a lot more realistic by adding heterogeneity, by adding elasto, plastic, visco, material properties, thermally, depending on the thermal gradient and things like that. But this is one of the problems we have in geophysics. We have the capability to make these very, very complicated, but we don't have the evidence to support those complexities because we don't have the resolution in our imaging. So we could make really realistic models, but what is realistic? We don't have the details of the heterogeneity and things like that. So we're in this sort of weird transition phase where the computers are better, the software is better, the models are better, we know the maths, but we just don't know what's down there, so we don't know how to make it realistic. But we are trying, we're doing some models. So this is an example of kind of magma mixing within, again, we've got this kind of bubble. Physicists primarily, so we keep it simple, we like spheres. So here you've got different types of rock crystals essentially, and you sort of inject something in, and you leave it for some time, and you see how it mixes. And some of these you can see, we've got crystals kind of accumulating at the bottom, and the hotter stuff going to the top, possibly the gas accumulating at the top. Okay, so that's kind of a very quick whistle-stop tour of the magma accumulation zone. Now we're going to talk about what happens as the magma comes to the surface, because there's a lot of very interesting changes happen during that time. So we've got 5 different examples of, these are conceptual models of what might happen when magma starts coming to the surface. So we start over here, down this end, we've got our basaltic magma. So this is runny, this is bright red, this is hot. So there are bubbles, there aren't that many crystals. So low viscosity, relatively low viscosity. What we have here is a decoupled flow. So the bubbles are moving faster than the liquid. And as the magma rises, obviously the pressure decreases. So not only do the bubbles grow, but more of the gas comes out of solution. So you've got sort of the just dynamics of bubbles growing with less pressure, but you've also got added gas. You've got some pearlescence of bubbles as well, and you've got some shearing of the bubbles because of so you'll have more friction on the edges, less friction in the middle. But because the lava is runny, it can flow. And so this is a fairly steady state. In a similar sort of setup, again, these are open systems as well, so we're saying that the crater is open, stuff can come out easily. In a very similar chemistry environment, we have where the bubbles coalesce enough, you get these kind of slugs, is what we call them. So they're big bubbles. Sometimes they take up the entire conduit, and when they get to the surface, they burst. So we call this kind of strombolian activity after, obviously, stromboli, where it's kind of just periodically you get these kind of little fountains of lava. So these are the beautiful ones. You know, this is Kilauea volcano in Hawaii. This is stromboli. These are niacin-touristic. Then we get down to this end. Again, this is fairly low viscosity, but what happens here is there aren't many bubbles to start with. This has come up really quickly, so the bubbles haven't really had time to form. And so as it ascends quickly, there's a high ascent rate, and you get this lava fountain at the top. So you've got lots of stuff coming out, and the bubbles and the sheer velocity makes a fountain, which, again, quite touristic, but a bit more dangerous. These are the ones where things go bang. So here you've got a much stickier magma. So you've got more crystals, it's colder, and potentially more exhaled gas as well. And in this case, it's actually a coupled ascent because it's so sticky that the bubbles can't get through. So you get to, in this case here, it's a closed system. We've got a magma dome here. And so things get stuck. And the bubbles have nowhere to go, and so they escape through cracks in the rock. And you're left with something that doesn't have a lot of gas left. So it's very sticky, and it does come out, but it's more like toothpaste. So it creates what we call a lava dome. And this is a fairly steady state. There are examples of this where the dome just kind of, it creates like spines, and it just kind of keeps flowing. But it's steady, but unstable, if that makes sense. Because then this can happen. If this becomes unstable and there becomes a pathway for the gas upwards, so sometimes due to gravity, that dome will collapse. We end up with fragmentation. And so at this point, we have this coupled flow, it's very sticky stuff, it's coming up pretty quickly. At a certain point, those bubbles will become so large that they overtake the volume of the liquid, and everything kind of shatters. So the liquid at this point is so thin, it becomes glass, it solidifies, the bubbles burst, coalesce, those the glass films shatter, and that's how you get volcanic ash. So at this point, this is where that happens. So you get these bubbles coming up, getting bigger. All of a sudden, the bubbles overtake the liquid, and you get ash, gas, pyroclasts coming out there. So very, very sticky, very dangerous, very sort of runny, touristic, but in all cases, you've got this kind of system where you've got crystals and gas bubbles and lava, the liquid bit. And in some cases they're coupled, in some cases they're not. So how do we know this? Well, we can look at the geophysics. So with the magma ascent, it's mainly seismicity that we're using in this case. So these are the actual earthquakes that are happening. So sometimes if you have a closed system, the magma has to actually break through the rock. And so you can see the cracking of the rock, and we can measure those and locate them, and those are the earthquakes that tell us where the magma is going. In some cases, we have different types of seismicity. So I don't have a slide for this, unfortunately, but we tend to have different types of earthquakes depending on what's causing it. So if we have rock breaking, then we have a high frequency earthquake. If there's an open path, but there's fluid going through, we tend to have a lower frequency earthquake. And sometimes if that happens continuously, we have like a harmonic tremor. It's kind of just like a pipe organ. You just sending the fluid through a pipe at a constant speed, you get a note. But we also get tremor from the actual eruption itself, but that's usually non-harmonic. It's all of that. So this is an example, I think, from Iceland, where this is seismic moment. So it's the amount of energy that was released. And you can see here that there was sort of slow build-up of seismic activity, and then at a certain point, there's a lot of seismicity, there's a large earthquake, and that's when the eruption started. So if we can trace this, locate it, we know where the magma might come out of the ground. There's also sort of geological erupted products that we can look at the processes that happen. The problem with the eruption, the magma ascent, is that often it will happen very quickly. And so we don't have very good resolution. It's also a lot smaller area than some of the geophysical imaging that we were talking about as well. So it's very difficult to see geophysically. Mainly what we have to do is, in hindsight, analyze the seismicity and look at the erupted products after the fact. But there's loads of modelling for this. So bubble ascent is one of the big ones that has been modelled. So we've got various models of bubbles rising, bubbles growing, bubbles interacting with different bits of the magma, shockwave dynamics. So this is how they cause earthquakes. And then you've got different, like how you make a slug or a bubble swarm, how these ascend, and whether different gases respond in different ways, because we tend to have CO2 exalts deeper, and things like sulfur dioxide exalt shallower. So by looking at the gas that's erupted, we can tell the depths and the pressures of some of these processes that are going on. And here's another example. This is convection. So this is single phase, but just looking at the temperatures of what's happening as well. Okay, eruptions. Eruptions are a lot easier because we can see them. So we've got a lot more data with eruptions, and So our observations are erupted products, but also we can actually see what's happening. We can look at it on cameras, we can look at thermal cameras, and there's a lot of what we know about eruptions is from the modelling. So this is an example at Vesuvius, where we've got kind of, it's not very good resolution on here, I'm afraid, sorry about that, but this is a big explosion. You've got kind of the ash, you've got different species of gas in there. One of the big ones is water. So you've got water, you've got CO2, you've got ash, and then we have what's called a column collapse, where the weight of, so everything's coming out really quickly, it's entraining cold air as it goes up, and then the weight of the ash inside the column becomes too much and it sort of collapses, and that's where you get the pyroclastic flows. So the pyroclastic flows themselves are a mixture of gas and ash and sometimes larger boulders, but they can be sort of analogous to like avalanches and things like that, which is hot. And so yeah, so there are lots of analogies that we can make with these geysers. So when you just have sort of superheated water, so you've got the kind of the steam and various other things there. So yeah, so here you've got the column collapse, and then you can see you've got the different pyroclastic flows coming out there. And then, once stuff gets further up into the atmosphere, you've got the interaction with various layers in the stratosphere, you've got the interaction with existing water in the atmosphere as well. And so we can use satellites to monitor where the plumes go. So we can look at temperature, we can look at different gas phases, and we can look at like the ash particles as well, and obviously the weather. So you can see, we can track and test and remodel. So this is an example of the ash cloud from an eruption in Alaska, Chilliwack. So you can see the ground deposits. So we know which direction the wind is blowing, for example. This is the concentration at flight level. Obviously, when it gets to this stage, very interested in the ash in the atmosphere because of planes. And particularly, there's a lot of planes going over Alaska. So even though not many people live there, there's a lot of monitoring goes on because of its a major air route. But the volcanoes out here, they've got like one seismometer on it, that. But it's what happens after they've erupted is more interesting because of the air traffic. And luckily enough, we now have satellites and we can see what's happening. So once stuff comes out of the ground, we have a better handle on it. It's a bit simpler. But, well, I suppose the other thing I haven't mentioned, there's a couple of hazards that I haven't mentioned with the actual eruption. So we have the actual lava flows themselves, which can be really interesting. I spent a couple of years in Hawaii, and just the transition between two types of lava flows I found really fascinating. The two main types of lava in Hawaii are called a'a and pohoihoi. A'a is the kind of really spiky blocks, and it's actually called a'a because that's the sound you make if you try and walk on it barefoot. And we call it clankery. So it kind of it flows slowly, kind of like a bulldozer, and the sound it makes is very clanky. Then you have pohoihoi, which is the beautiful rivers, and as it cools, you get this ropey formation. So it kind of makes ripples, and the ripples, so it's still flowing underneath, and you get this skin, and it kind of looks like twisted ropes on the top. And I always thought that it would become RR once it cools down and it gets a bit stickier and it's dissolved a lot of its gas. But actually, it's all to do with the strain rate. And there are cases where you have a Vohoi flow and then it hits a steep slope. And it turns into RR going over the slope. And then it turns back into Vohoi. And it's just fascinating because it's sort of solidified and gone all clanky and exhausted a lot of its gas, but then it turns back into Vohoi because it's a lower strain rate. So that's, and you know, there's lots of research going into modelling lava flows around objects and seeing if we can cool it down with hoses and things like that. There was an interesting situation. There was a big eruption a few years ago that was heading towards a populated area, and somebody built a wall to try and protect their house, which actually can work, but insurance-wise, there was a whole can of worms, because if you deflect it from your property, you're deflecting it onto somebody else's property, and is it then an act of God? So you have to take it all down. So that's an interesting aspect, and once you get the crust on it, it still inflates as well because the gas still dissolves. And then the other, I suppose the other hazard that's really relevant are lahars. So lahars are water-based mud flows essentially. So often this will happen when there's an ice-covered volcano, and the magma, or the lava, once it's erupted, interacts with the ice, melts the ice, you get a lot of water mixed with ash, and you get this kind of slurry flow. This also happens in places where they have monsoons. So Philippines is a terrible example of where there's killed a lot of people, where there was an eruption and there was a lot of ash, but then the monsoon came, it remobilized all the ash, and there were enormous mudslides that were just devastating villages. So lots of modelling again with that, and the dynamics of lahars is slightly different to normal floods as well. I just wanted to mention, you can't really talk about volcanoes without talking about hydrothermal phenomena. Obviously, there's a lot of modelling done around hydrothermal phenomena because of hydrothermal energy. So people can actually exploit the hydrothermal energy, so they want to know so there's more money there. So this is an example of some kind of heat flow maps around some hydrothermal areas. And I do have a quick amount of time to show you a case study. So as I said, I've spent a lot of time in Hawaii. I did a postdoc there, and I want to tell you about Kilauea Volcano. So Kilauea Volcano is one of the youngest, is the youngest and most active volcano on the Big Island of Hawaii. And this is kind of the cartoon of what we think it looks like. So this is we call it the summit. It's a shield volcano, so it's not pointy, but it still has a highest point. So we've got a deeper magma reservoir, shallower magma reservoir, a place where it was erupting. We've got a lava lake. Interestingly, here, even though the magma comes to the surface, it degasses, it cools down, but then it goes back down again. It doesn't actually come out of the ground here. It comes back down, and then at some point, we don't know where really, it moves along the East Rift Zone. And here we get fissure eruptions, and there's well, up until 2018, there was a persistently erupting cone called Pu'u'o, and then it erupts from there, and then it travels down to the sea, sometimes making lava tubes. So that's kind of the status quo between 2008 and 2018. And then in 2018, let's see if this is going to work. This happened where it wasn't supposed to. This happened further down. Around people's houses, and it was literally to people's back gardens. You can see it's very difficult to get a sense of scale, but these mountains are about a couple of 100 meters high. So that And this, it got bigger and bigger and bigger, and unfortunately the video of the later events was too big to put on here. But what this is, before I start it, I'll talk through this, hopefully this will work. This is Kilauea, so this is a map of Kilauea. The black triangles are our sensors, so this is one of the best monitored volcanoes in the world. When it started erupting, we went and put more sensors out. There will be dots that appear on here to show where the earthquakes were, and these are depth sections. So that dense cluster of black triangles, that's the summit where the caldera was, and then this little cluster here is where Puerto was. But over on this tip over here, none of those sensors were there previously. This is a populated area, and this is where the eruption happened in 2018. And it was very interesting for a lot of reasons. So let's see if this is going to work. Great, it's working. So this was sort of business as usual. So got lots of seismicity at the summit, not much elsewhere. And then all of a sudden, you see a quick propagation of seismicity down towards the Lower East Rift Zone. And then a large earthquake there it goes. And then there's a big earthquake with a load of aftershocks. And so at this point, magma is withdrawing from the summit, magma is withdrawing from Puerto, and is all coming out at the end here. Now, interestingly, once this eruption has started and established itself, there's basically no seismicity up this end. There's no more rock breaking or anything like that. The magma is able to flow uninhibited. But what we've got up here are pulses of earthquakes. I don't know if you can see that. It's coming and going, coming and going. And that happened about 12 hours for 3 months. As the eruption out here was happening, the actual eruption itself was really interesting because it had some of the highest flow rates of any basaltic eruption. So some of the lava rivers flowed the fastest that we've ever seen. There was interaction with the sea, which makes things interesting. But what I'm really interested in is what was going on at the summit here. And also, it just stopped. You get to 4th of August, and the eruption stopped, the gas stopped, the seismicity stopped, everything stopped. It was eerie. Less seismicity than there was before.
These are like earthquakes. Right?
These are earthquakes. These are small earthquakes. Well, these are earthquakes between magnitude 1 and 7. There was only one magnitude 7. Most of these are around magnitude 2 or 3.
Maybe it's broken. Is it earthquake or is it waves that you measure?
We measure the waves on several.
Like not be related to any motion. The global explosion. Is it clear that these are considered as an earthquake?
So we look at the frequency of the vibrations that we get, and most of these are rock breaking. The seismicity that happens at the summit, the actual seismicity there was really interesting because we had a build-up of magnitude 2 and 3 earthquakes. They happen more and more and more. Because normally, in an earthquake situation where it's all just solid rock, you have a big earthquake and then you have aftershocks because of the stress realignment and things. But in this case, we were having more and more and more earthquakes, and it culminated in a magnitude 5 earthquake and then stopped. And then more and more and more, magnitude 5 earthquake and stopped. And it's that magnitude 5 earthquake which was a bit different from everything else. So we've got some models that let's see if I can, what's this video? Okay, so before I play that, so what we think was happening was the caldera had a big magma reservoir underneath it. And as the magma was withdrawn, the lid of the caldera was falling. And so that the caldera lid was being supported by friction around the edges. And the small earthquakes were the the increase in stress, because that lid was no longer being supported. We were withdrawing the magma that was supporting that lid, and it got to a certain point, and that lid collapsed and was supported again. And then, so there was no seismicity, and then as the magma withdrew, the seismicity built up around the edges, and then there was a collapse. So that actual, the magnitude 5 collapses were really interesting. They were what we call, well, they were part implosion, but they were part compensated linear vector dipole, which is kind of where there's a change in the moment, the seismic moment shows that there wasn't a volume change, but there was a sort of, it was like a pancake, like squashing and everything coming out the sides. And it was low frequency as well, so there was fluid involved in that. But this always gives me chills. So this is the Hawaiian Volcano Observatory. This is one of these magnitude 5 earthquakes. And this is the view from a hotel that obviously wasn't populated at this point, looking at the caldera. So there's the seismic waves, but then, I don't know if you'll be able to hear it, there's this growing sound, and the ash clouds grow, and that's the actual collapse of the caldera. And each of these collapses was up to 8 meters of substance of the caldera floor in one go. This is the seismicity. So these are number of earthquakes counted. So this doesn't show the size of the earthquakes, but it's basically a sawtooth. You can see it building up and then dropping, building up and dropping. And then here you can see everything just stopped. So this was that. So about every 12 hours you had all of these collapses. So each of these collapses is between sort of 3 and 8 meters. And so the total collapse of the caldera floor was about 200 meters in total. Over 3 months. And here is a video, a time lapse of that caldera. Oh no, this is just a video of the caldera and sort of mid collapse. Oh, there we go. Okay, so that's what I have. Some of the other videos were a bit too big. So yeah, there's still a lot of questions. I think one of the really interesting questions about this eruption was, why did it stop? Did the magma level just drop so low that it just wasn't supplying it anymore? Or did the pressure in the magma drop? So a lot of the time we model this with like a hydraulic head in an open system, but obviously because it's magma rather than water, it's a bit different. Why did the eruption start? It had 2 open vents. It was perfectly happy erupting in these 2 places for 10 years, and then all of a sudden, even though there were still open vents, it decided to go somewhere that hadn't erupted for 50 years. Yeah, so what was happening at the summit? Why did it start erupting? Why did it stop erupting? Still some questions that do involve multi-phase flows. Definitely.
Thanks very much, Jess. It's really interesting.
Well, why did it stop? What are the rheological properties of magma? Is it simply that it's sort of it goes beyond below a yield stress, perhaps, the flow rate, and then the magma doesn't flow anymore? Is it sort of a viscoelastic or viscoplastic fluid? How am I supposed to imagine that?
Yes to all of those.
Okay.
It completely depends on the amount of bubbles and crystals in it. I don't know is the answer.
I suppose also on the pressure and the temperature, right?
Pressure pressure and temperature as well. Yeah, absolutely. So my conceptual model I have two conceptual models for why this particular eruption stopped. One, if we go back to the kind of the cartoon of, and you guys might be able to tell me that I'm completely like in the wrong ballpark of this, but one of my conceptual models is, so it was erupting, so here. So this decided not to erupt here, decided not to erupt there, and carried on and started erupting here, right? One of my conceptual models is that once this all got drained down to here, and got lower than this point, basically, there just wasn't, it was draining faster than it was recharging. And there just wasn't any magma, all of a sudden. But then I would have expected us to see like a waning as the pressure got lower. So that's one possibility. The other possibility is that, so this, after a while, this was closed, it was erupting over here for 3 months. But there are dynamic stresses in the rock itself, so sort of confining pressures. And I wondered whether the really sharp stop that we saw could have been to do with the fact that this conduit had pressure, magma was flowing, and then all of a sudden the confining pressure overwhelmed the pressure within the conduit and it just kind of snapped closed.
So the conduit collapsed?
The conduit collapsed, yeah, basically. I mean, we don't have any geophysical evidence that that happened. There wasn't like seismic waves associated with that. But yeah, those are the only two things I can even think of. I don't know how else, what else would make it stop so suddenly like that. But yeah, so when it's down here, it's very runny, very, very runny. Because this is a basaltic system as well. So we know there are examples where they've drilled into pockets of rhyolite where there's been an unerupted product, and it's a magma pocket that sat there for millennia, and it's just cooled down and crystallized and become rhyolite, but become very sort of silica rich. But this is brand new stuff. It's come from deep. It's very hot. It does have volatiles in it, but they're all dissolved until it gets out of the ground. So it's more simple in that way. I didn't answer your question.
No, it's interesting.
Yeah, so I had a question, a completely different one. So of lava flow. So is any material trained in this flow? Is it flowing down? Is it a lot of material, or?
It depends what it's flowing over, I suppose. But, so there have been. It's very rare that you have thermal erosion with a lava flow. You can have thermal erosion, but mostly it deposits rather than picks
So
things
it
up.
flows over rocks or?
Yeah, it usually leaves stuff behind and kind of there. I'm just doing arm waving things now, so I can't remember the name of it, but it's called kind of the top moves fast and the bottom doesn't move, so it doesn't really pick things up. Whereas a pyroclastic flow will pick things up.
Yeah.
The lava flow tends not to.
So, going back to the previous question, what you showed reminds me of, like, in mountains, water springs, they appear at a certain point so that something happens, and that either disappears, so you find it in some other place, because water, like magma, follows the path of least resistance, right?
Yeah.
So the pressure changes, as
Yeah.
you said, and all of a sudden it decides to go someplace else because it's impossible to find its way all the way up to
Yeah.
the original crevice. So
Yeah.
you find it someplace else. It's like water. In a way, only with gases. So it's easier in a way to find it, because
Yeah.
people lose water springs in
Yeah.
mountains in this way. So just one comment.
Yeah, no, absolutely. It's still difficult to get your head around, isn't it, though, where, it was open. We could see the lava here. It was completely open. And it was definitely closed in this direction. But And this is 40 kilometers. But it started to withdraw from here and erupt down here.
It's easier to go that way, I guess. Less resistance, less.
I mean, possibly, but it's solid rock that's not been cracked for.
It must be easier,
50.
otherwise it would be.
It has to be easier. It has to
But
be
it's the
easier.
question is why.
Yeah.
Because it's the pressure's lower, there's more, well,
Yeah. No, I mean,
Pressure loss.
it is potentially downhill in this direction. Well, so this magma reservoir we think is about sea level. So this is about 1 kilometer above sea level. This is about sea level. This is, we think, about 5 kilometers deep.
surely.
But from here to here is downhill. Not a lot. But yeah, so they're happy models of kind of why it got blocked here. The other interesting thing is, and this was, there was a large earthquake, and the large earthquake was actually to do with the whole side of the island moving, and it's actually gravity driven, because as the volcano grows, it flexes the crust, the oceanic crust, but as the mountains get too tall, gravity is pulling them down, and so the transition between the oceanic crust and the volcanic pile, we call the décollement, and it's quite slippery because it has kind of ocean sediments in between, and so there's the ocean crust, there's the volcano, and this section kind of moves in that direction because it's getting too heavy. And so there's been this age-old debate, this sort of chicken and egg thing. Sometimes where this travels down rift is actually a weak point between the bit that's moving and the bit that's not moving. So does the magma push it and that bit moves, or does that bit move, make space, and then the magma can make use of that space? And sometimes that happens quickly, and that's a magnitude 6 or 7 earthquake. Sometimes that happens slowly, and it's what we call a slow slip event. So you can see it on GPS, you can't see it with the seismometers. And previous eruptions have been associated with these slow slip events, but they happen roughly at the same time. This one, the magma migrated down rift before that earthquake. So once the magma had got there, it pushed its way through. There was a magnitude 7 earthquake, that made more space. So that's why it was flowing nicely after that. But the initial pushing through, it pushed the rock so much that it was a magnitude 6 earthquake.
Just one small second.
Yeah.
If you go back to the slide you showed with the flow patterns, did you try to, this entire literature in two-phase flow, where you have slag flow or stratified flow, or if you go back to
Where was that?
well, perhaps in the previous slide,
This one?
no, before that.
What that?
Yes.
That one?
Yes.
Okay.
That's flow patterns of two-phase flow. You have slag flow, you have like a two-phase flow where the gas is in the middle or outside.
Yeah.
So there's an entire, of course, literature in two-phase flow
Yeah.
for tube flow, of course.
Yeah.
So tube is like two-phase flow, but there's heat transfer as well. Did you try to model or look at whether that explains?
Well, even the strombolian activity, that looks like spouting of a fluidized bed.
Yes, or it can also be like a trickle bed motion, because you have solids as well. So there is, it is a new genre, the way you present it. It's like two-phase flow, you have heat transfer,
Yeah.
and you perhaps you can identify flow patterns depending on the pressure.
Yeah, absolutely. Yeah, and with a conduit like this, it's rather, you've got gravity just moving, just acting in one direction, and
But you have pressure-driven flow, right?
yes, pressure-driven flow, you've got gravity. If you have lateral migration, you've got a few other parameters in there, because you've also got an overpressure, and you've got kind of the tectonic stresses